We're going to look at Chapter 1 on function sense in Cluster 1 today with modeling with functions. First, before we begin, I'm going to pull over my MyMathLab window. If you don't yet have your paper textbook, you can go into the MyMathLab area and to the e-text contents, and here you can view the e-text for your course. You can go section by section or you can open it at the beginning. I'm going to start with section 1, so it will open directly to this activity. If I open the book, I can navigate there from the main page of the book as well. When the book opens, you would see the same thing that I have up on screen here from my paper book. This book behind my MyMathLab window is my paper copy of the book. You should definitely pick up your paper copy of the book from the bookstore. It's already paid for as part of your course fees. If you don't have it, you're not taking advantage of dollars that you've already paid. So please do pick that up as soon as possible. But in the meantime, if you're still waiting for that to be shipped to you, then I recommend getting into the e-text and following along with the videos here. And you can even print these pages. They do print one at a time. If you go over to where your initials are at the top, you can print the page, though it's not possible to print the entire section all at once, as far as I know. You would have to go in and print page 1, and then again, when you get to page 2, you can print page 2, but it would allow you to get a paper version while you're waiting for your textbook. So just wanted to share that those pages were available. And let's go into the notes here for section 1.1. So we're going to talk about in section 1.1, we're going to talk about identifying input and output in situations involving two variables. We're going to identify a functional relationship between two variables. We'll talk about independent and dependent variables and how those relate to the definitions of input and output as well. And then we'll look at functions that are defined numerical as a table. And we'll also look at using function notation, and input and output values written as ordered pairs is our last part of the objective list here. All right, so in the first situation, we are talking about a number of cars in a parking lot at a particular time. And this table of information right here. So this is our first function that is defined numerically. Well, we're actually going to discover whether or not it is a function when we get to the next page. But this is a numerical definition of an equation or perhaps function. We want to determine if it is a function. The definition for a function will appear on one of the next few pages. So we'll get to the next page here for our first set of questions. All right, so on to page 2. All right, so we've got some definitions again. We are starting to talk about variables. A variable is usually represented by a letter or quantity that may change in value from one instance to another. Typically, one variable is the input, one variable is the output, and the output value corresponds to or is determined by the input. So we'll underline that piece there as well. We can tell which one is the output because it is determined by the input. All right, so for the data in the preceding table, let time of day be the input variable, and then we'll let the number of cars be the output variable. So time is the input, cars is the output. And it asks us first for an input of 10 a.m., how many cars are in the parking lot? So you need to flip back and forth between the preceding page to be able to answer this question. I'm going to pull my other book, my MyMathLab book, over so that I can see both of these at the same time, and then I'll be able to answer the question. So for 10 a.m., I can see that there were 426 cars in the parking lot. So I will write that in. For an input of 10 a.m., there were 426 cars. And for an input of 5 p.m., there were 302, as you can see here, 302 cars in the parking lot. Okay. Now, next they ask us for each input time of day, how many different outputs numbers of cars are there? So at 7 a.m., there are 24 cars, but there's only one option. There's not 24 cars some days and like 82 other days. It's just there's one particular output for 7 a.m. And so that's what we want to say here, is that for each input, there is one output. So I didn't have an option for how many cars we were to answer for each of parts A and B. There was only one correct answer based on the table. There's only one answer, whatever it happens to be. So for each input, there is one output. Oops, there is one output. Okay, so that leads us towards the definition of a function here. A function is a correspondence between an input and output variable that assigns a single output variable to each input value. So this up here is a function, and we want to, in number 2, use the results from problem 1 to explain how the data fits the description of a function. So for each time, which is the input, corresponds with exactly one output. And that satisfies the definition of function because we have a single output for each of our inputs. So that table from page 1 does numerically define a function. Okay, so I'm going to skip through some of the examples as we work through the book, but make sure that every time I skip an example that you pause me and read through the example. I'll talk about this first one right here. This one is a table that talks about the input as the date and the output as the temperature. They reorganize the same table on the next page, just organized vertically instead of horizontally. It's the same information though. And what we can see here from either orientation is that each input goes to just one output, and so this is a function. So as they conclude here, this is a function because the dates correspond to just one temperature each. So it is a function. All right, now they've taken this same table in our next piece of work here, and they have flipped it just to see if they had tried to relate temperature to date, if it would still be a function. But what happens here is that 30 had two different dates where the temperature was 30. And so this is not a function. Date is not a function of temperature. In this order, we can't use temperature to get a single date prediction. It's not true. So it's not a function. So the output, the date, is not a function of the temperature. Right? But the output temperature is a function of date in this order. Notice how we say output first. So the output is a function of the input. Because the output is the thing that only occurs once per input. So we do phrase it in terms of output first there. Okay, so next they want us to interchange the input and output in the parking lot situation and determine if it is going to be a function. So we're not going to actually write the table, we're going to imagine the interchange. So if I had imagined the interchange up here, thinking about this backwards, see how I can see that this would not have been a function in the reverse because 30 has two different inputs that were associated with it. So it is a function in one direction, but not a function in the other. So let's take a look at our table. We don't have space to rewrite the table in the other direction, but we're going to scan our output list and see if there are any outputs. Wait a minute, I just found one. That 384, that is two different inputs associated with it. So it is not going to be a function in the other order. So we will say that time of day is not a function of the number of cars. Oops. It's not a function of the number of cars. And our reason for this would be that the number of cars, I found one of them at 384 and it pointed to 9 a.m. and it also pointed to 1 p.m. and I believe it also points to 7 p.m. So there are three things that it points to. There only have to be more than one. There only have to be two, but there are three things that it points to, and so it would not be a function in this direction. It does not have a unique, output per input. So we'll make ourselves a note that the output is not unique. Output being time is not unique. All right. All right, so on to our next page. Again, please read through example 2. We're going to skip and look at number 4. You get a chance to read through example 2 on your own. Let me get our digital book out of the way there. All right, and I've already filled in a tiny bit of the section when I was doing this class in person, but we can definitely talk about the piece I've already filled in addition to the other pieces. So first, we want to determine whether each situation describes a function and give a reason. So for the first, for a part-time student, the amount of tuition you have to pay is a function of the number of credits. Is this a function or not a function? So you would want to ask yourself, if you took 4 credits, would it be the same as if you took 4 credits this semester or 4 credits next semester? As long as the rates stay the same at this college, would your tuition be the same? And so this one should be yes for the tuition based on your credits. Yes, because for a given number of credits and input, there should be exactly one corresponding tuition amount. Yes. So for a given number of credits, there is one tuition amount. Now, tuition is usually a per credit fee. There are other things to keep in mind. Courses have course fees that may vary, but the tuition amount, that's not going to vary. There's a set amount of tuition per credit, so no matter what, it should cost the same amount for the credit portion of the tuition. Fees are separate to this, but the tuition should be the same for any 4 credits of class. Part B asks us, the amount of calories you burn while spinning at your local gym is a function of the time you spin. So if you spin for 60 minutes, do you always burn the exact same calories? And so this one is not going to be a function. And one example might be that the speed at which you spin might vary. But even if we took away the varying of the speed, let's say we spun at a high spin the whole time, would it always be exactly 300 calories, or might it be 302 next time, or 299? Even if you're trying to spin at a high speed, you're not going to be able to burn exactly the same amount of calories every single time. Bodies just don't work that way. So this one's not a function. In part C, the amount of interest owed at a college on a college loan is a function of the amount that we borrowed. This one is a function. There is a relationship that if you borrow a certain amount, there will be exactly one amount of interest that you owed. It won't be 2 different things where you simultaneously owe 2 different things. There will be one thing that you owe. Okay? The output is not simultaneously 2 different things. So we have a function. So this is yes. It is a function because for any given amount borrowed, there's exactly one corresponding amount of interest owed. For any amount borrowed, there is exactly one amount of interest owed. And last here, the value of a used truck is a function of its age. Well, if you had a truck and it was 8 years old and you had two people come to look at it, would they offer you exactly the same amount for it on the same day? Not necessarily, right? So it might not have a singular value. You could have two different offers on the same day. So the age of the truck is not going to be the sole deciding factor on the value of the truck. So we're going to say no on this one. So for a specific age, you could be offered multiple prices for your truck. Okay. So at a specific age or at any given age, the truck could be worth more than one of value. And so we're thinking of like more than one buyer might offer you a different price. Somebody might say, "Hey, I'll give you 2,000 for your truck." Somebody else might come by and say, "I'll give you 2,100 for your truck." So it might be different at the same age for that truck's value. So it could have more than one value, even if its age is not changing. So there is a relationship between the age and the value, but it's not a function. All right. So definition. In our next definition here, the relationship between two variables is a function if it is a function. So first of all, we're going to note that if it is a function, then we're going to call the input variable the independent variable. So input variable is the independent variable there, and we're going to call the output variable the dependent variable. And usually we'll let the letter X represent the input variable, and again, we usually let the letter Y represent the output variable. And so again, in this case, X is our independent variable and Y is our dependent variable. We don't always use the letters X and Y, but in a generic situation, we can assume that X is always the independent variable and Y is always the dependent variable. All right, so continuing on for number 5, the independent variable in example 1 is a date. The dependent is a temperature. Identify the independent and dependent in example 2. So I got to go back and look at example 2. Example 2 down here is about the amount of postage for a letter is a function of the weight of the letter. So remember that the amount of postage is a function. That means that this one is our output, is a function of the weight of the letter. So this one is our input. So once I identify the independent and the dependent, the independent is going to be our input. That's going to be the weight of the letter. Go back and write over here. So the independent is the weight of the letter. And then the dependent was the amount of postage. All right. Defining functions numerically. So we've already seen a few functions that have been defined numerically. Oftentimes, you'll see things listed as a table of matching pairs. That is what a function defined numerically can look like. It can also be listed as a set of ordered pairs. So instead of a table, we could list them as ordered pairs. And ordered pairs consist of two numbers written in the form of input, comma, output value with those parentheses around them. The order is significant because the input has to go before the output, of course. All right. So on to our next page. Again, I'm going to skip example 3. Please read through it. A function may be defined numerically as a set of ordered pairs in which the first number always corresponds to the input. So first is our input value, and the second number in the ordered pair always corresponds with the output value. To be a function, no two ordered pairs have the same input with a different output. So to be a function, no two ordered pairs have the same input. So no same inputs with a different output. All right, so now we're going to use a 24-hour clock to write 3 ordered pairs for the parking lot situation. They've already shown me an example up here. So we're using a 24-hour clock because we need to make a difference between 9 a.m. and 9 p.m. So let me get our table back up here so we can look at it again. So they've done the one for 9 a.m. So I just need to write 3 other ordered pairs. So I'll start with 11 a.m. So let's say 11 a.m. would be 1100, just military time or in a 24-hour clock, comma 500, let me pull my book down a little bit, 538. Then noon would be 1200, comma 497. And then 1 p.m. is going to be 1300. So 1300, comma 384. So I started at 11, 12, 1, or 1100, 1200, 1300, just so we could see how that was going to continue counting up after 1 p.m. We have 1300, 1400, 1500, all the way until we get to 2300 at 11 o'clock p.m. So in example 1, the high temperature in Lake Placid is a function of the date. To convert to ordered pairs all of the values in that next table. Okay, so I'm going to keep my book up here so I can just see 2 pages at once. You can flip back and forth if you need to. Here is our Lake Placid data. Now it wants me to convert all of the values in this table to ordered pairs. So the first one is 125. The next one is 230. The next one is 332. I think the only reason they didn't ask us to do all of them in the previous question was that there were a lot in that first table, so it would have a lot of writing. We can do all of these here because there weren't as many values. So 424, 523, 627, and last we have 730. So we've converted those to ordered pair notation instead of table notation. So next we're going to talk about function notation. All right, function notation uses the letter F to name a function. It doesn't have to be, it could be G or H or any other letter. And if we have a situation where F is the name of the function, T is the name of the input, and C is the name of the output, in this situation it was our time in our cars, then the following simplification, really an abbreviation, is possible. So the number of cars in the parking lot is a function of, that's the equal sign, and the name of the function F, the time of the day. So this sentence right here, C equals F of T, says the same thing as this sentence up here. It's just our shorthand. It's our mathematical shorthand. The number of cars is a function of time. C is a function of T. Cars is a function of time. That's how I would read this. C is a function of T. Cars is a function of time, and we just have our mathematical shorthand for that. Okay, so again, the final thing is read is C equals F of T, meaning that the number of cars is a function of the time. Note that F of T does not mean F times T. This is not read as a multiplication. It's read as of being, same notation, those parentheses, but of meaning the input variable is your T. F is a function of time. So we'll definitely read this as C equals F of T. All right. So we are going to write some ordered pairs in function notation. So I want to rewrite the 3 examples in number 5 up here as ordered pairs. These ones are already in function notation. So when you are in function notation, the output is off by itself, the input is inside, and then the name of the function is our letter out front. So we have our output, name of the function, and our input. So our inputs, which go first in the ordered pair, is our 800 in this case. Also note that the input variable is often also called the argument of the function. I know I'm going to use that word argument later as we talk about the inside of certain functions, the input of certain functions. So just the definition of it right here. You'll start to hear that word argument from me later on in other sections. Okay, so getting a little glare here from my light. I can maybe lean into it. We have our first ordered pair. This is the output. So it actually goes second. So we're going to write this as 800, 212. Then we're going to write this as 1700, 302. Because the input goes first in the ordered pair. Maybe scooch that up a little bit. And the last one, the input, they flipped the notation on us here. The input is inside the function. So the input here is our 2100, 187. So pay attention to what is inside the parenthesis as the input goes first, and what is outside the function is the output goes in the second part of the ordered pair. Okay, and next, write the sentence explaining the meaning of f of 1600 equals 278 in the parking lot situation. I had to adjust my zoom there. Okay. So first of all, when I write time, most of us don't think in terms of a 24-hour clock. So I want to think about this 1600 minus 1200, which is noon, would be 400 or 4 p.m. So I'm just going to translate and figure out what 1600 means in terms of time. Remember, 12 is noon, then 13 is 1 p.m., 14 is 2 p.m., 15 is 3 p.m., and 16 is 4 p.m. So I can just subtract the 1200 to translate that into 400 or 4 p.m. So my sentence is going to say, at 4 p.m., there were 278 cars in the lot. Right? Referring to the table in example 1, determine g of 3, where g is the name of the temperature function. All right, so if this is my g function, 3 is the input. So once we determine g of 3, it means what is the output for g of 3? It is 32. So we can say that g of 3 equals 32. We're just reading the numeric function to determine the output for the input of 3. Write a sentence explaining the meaning of g of 5. I'm going to look back at my function over here. G was the temperature on a given date. So on the 5th, the temperature was 23 degrees. So the date is the 5th. So on the 5th, the temperature was 23 degrees. I'm going to assume it's degrees Fahrenheit. I believe it was from that table. Okay, on to our next question. If you work for an hourly wage, your gross pay is a function of the number of hours you work. Identify the input and the output. Okay, so gross pay is a function of the number of hours. So gross pay is the output. And the number of hours you work is the input. Okay, so identify the input and output. I just kind of did it here, but we could write this if we would like, that the input is the number of hours worked. And output is the gross pay. Now, when I identified those, I did it because I know that the output is always a function of the input. So if I find the is a function of, after the word of comes the input. Before the is a function part comes the output. So I know the order has to be in that way because of the way they phrase their sentence. Also, I know that my gross pay is controlled by how many hours I work. So my output depends on my input. All right. If I earn $10.50 per hour, complete the following table. Okay, so I'm going to grab my calculator. So I'm actually going to open up, this is just a web browser. And the calculator that I'm going to use is Desmos.com, which you'll be using a lot in this class, so start to get used to it. And just going to do the multiplications here. So it's $10.50 per hour. So I'm going to take $10.50 times 0 is 0, as you can already see. But now I'll multiply it by 3. $10.50 times 3 gives us $31.50. If I work for 5 hours, it would give me $52.50. If I work for 7 hours, I would get $73.50. If I work for 10 hours, I would get $105. And if I work for 12 hours, I would get $126. All right, so my calculator off to the side. Let n represent the number of hours worked, f of n represent the growth pay. Use a table to determine f of 5. Okay, so f of 5 is going to equal, from this value in the table, I can see that the output for an input of 5 is 52.50. So we're just restating the numeric function in function notation to call out a specific input-output pair. Write a sentence to explain the meaning of 10 equals 105. So if you work, 10 is the input, so 10 hours, you earn $105. Last example, number 11 here. The value of your car in dollars is a function of the number of miles driven. Explain the meaning of f of 52,000. Okay, so f of 52,000 is the output. I don't have the number for the output, but I know the output is f of $52,000. So f of 52,000 is the value of a car with 52,000 miles. I don't know what it's equal to, so I put, instead of putting the 52,000 in the output spot, I put the f of 52,000 in the output spot. But when I explain this, I want to explain what the output means. The output is the value, and what the input means. The input is the number of miles driven. At a particular coffee house, the cost in dollars of a cup of coffee is a function of the size of the cup. Explain the meaning of G of 12. So the output G of 12 is the cost, that's the output, of a 12-ounce coffee, since the input is the size in ounces. All right, so we hit the end. There's a summary. Make sure you read through your summary after each of the lessons and start making your notes for the course.